Hello again. We're continuing our work on Chapter 10, and this time we're going to be talking about the dissociation of water, Section 10.5. We're going to be talking about equilibrium, an equilibrium reaction, which is the auto-ionization of water. We've mentioned that water can act as an acid and a base, and it can do so by itself. And we're going to be putting some numbers on some of this process and introduce you to pH and the concentration, measures of the concentration of hydronium ion and hydroxide ion. And remember, H3O plus is referred to as hydronium ion. So you want to keep that in mind. We've said before the water is amphoteric, and here we're actually defining amphoteric. I've mentioned the term before, but it simply means that an amphoteric substance is one that can act either as an acid or as a base. And water is one of these. So in water, hydrogen ion can be transferred from one water molecule to another. One molecule is acting as an acid. Remember, it's a proton donor or a hydrogen ion donor, while the other acts as a base, which is a hydrogen ion acceptor. And an equilibrium is reached between these conjugate acid-base pairs. And you see in the reaction, you see two water molecules reacting, and then those are the reactants, and the products are a hydronium ion, H3O plus, and a hydroxide ion. This is a classic case of an amphoteric substance. It's one of water's fairly remarkable properties. Water is a rather remarkable substance. It does have quite a few properties that make it essential for life, that make it possible for life to exist. It's actually a very reactive molecule, and it has some properties that are, it's freezing behavior, where the liquid is actually denser than the solid. That's one of them, which makes aquatic life possible in regions that go below freezing. There's a lot of interesting things about water. Now, we can actually measure these dissociations. Remember that if you look at that, you have water, two water molecules are breaking apart and forming other molecules or ions. We can put a number on how far that goes. This can be measured. And it isn't very far. Water is a very weak acid and a very weak base at the same time. And in pure water, you see the concentrations given here is 1.0 times 10 to the minus 7th molar. That's 10 to the minus 7th. That's 1/10,000,000th molar, I believe it is. 10 to the minus 7th. It's very small. And we define, in the previous presentation, you saw me define the equilibrium constant. And this is a modification of an equilibrium constant. And this is what we use for water. It's called the K sub W. It's the dissociation constant of water. And in water, at 25 degrees Celsius, pure water has the dissociation constant equal to 1.0 times 10 to the minus 14th, which is the product of the concentrations of hydronium ion and hydroxide ion. Now, this is going to be true. That constant is going to be true in all water solutions, where it's essentially a solution of something in water. Water is by far the largest species present, and you're going to see that 1 times 10 to the minus 14th is going to be true for all water solutions. That has important consequences. This dissociation expression is defined as the product of the concentrations of hydronium ion and hydroxide ion, and it's equal to 1 times 10 to the minus 14th. It's not so much defined as the product of the concentrations, it is the product of the concentrations at 25 degrees Celsius. And there's, as I said, it's always going to be 1 times 10 to the minus 14th. I'll go back to this KW is defined as 1.0 times 10 to the minus 14th is defined as K sub W. I think that would be a little more accurate, but all the same. Here's the point. When the concentrations of hydronium ion and hydroxide ion are equal, the solution is neutral. So each has a concentration of 1 times 10 to the minus 7th molar. But you can have more hydrogen ion and less hydroxide, or less hydronium ion and more hydroxide. In one case where the H3O plus concentration is greater than the hydroxide, the solution is acidic. And where the hydroxide ion is greater than the hydronium ion, the solution is basic. This is always going to, but it's always going to have that product of 1 times 10 to the minus 14. So if you add an acidic material to water, if you add a proton donor, a hydrogen ion donor, if you add sulfuric acid, for example, or hydrofluoric acid, even if it's a weak acid, you're going to increase the hydrogen ion concentration or hydronium ion concentration, and you're going to reduce the hydroxide ion concentration. If you add a base, something like sodium hydroxide or even ammonia, you're going to increase the hydroxide ion concentration, and the hydronium ion concentration is going to drop. Now, again, pure water is neutral. The concentrations of hydronium ion and hydroxide ion are the same, so there's not an excess of one or the other. So those quantities are equal, so pure water is neutral. There's no acidic, basic, and neutral. Simply means that acidic, you have an excess of hydronium ion. Neutral, the two are equal, and basic, you have an excess of hydroxide ion. And we'll see how that works out. You add an acid in pure water, as I just said, you'll increase the hydrogen ion concentration, which will cause the hydronium ion the hydrogen ion or hydronium ion concentration to exceed 1 times 10 to the minus 7th. It's also going to decrease the hydroxide ion concentration. You're still going to have that K sub W is going to be 1 times 10 to the minus 14th, but the actual quantities that are being multiplied are going to be a little different, and we'll see some of that shortly. In fact, you're going to calculate some of that shortly. And as I said, you add a base to pure water, it's going to increase the hydroxide ion concentration. It's going to cause the hydroxide to exceed 1 times 10 to the minus 7th molar. And of course, it's going to decrease the hydronium ion concentration. This is, I think, fairly simple. And some of these simple concepts are what get you in trouble. So it's not so much that it's a complicated situation. It's the numbers we use and how we use the numbers, as you're going to see, can be something that you really have to look at and you really have to study. So here's another slide which describes how these things work out. The acidic solution has a greater hydronium concentration. Their hydronium and hydroxide are equal in a neutral solution, and hydroxide is in excess in a basic solution. So you want to remember those. We have examples here of some acidic, basic, and neutral solutions, just so you can see what we're talking about. Neutral solution we've already defined as the hydronium ion and hydroxide ion are equal in concentration. And so we've also given you as 1.0 times 10 to the minus 7th molar, both of them, hydronium ion and hydroxide ion, at 25 degrees Celsius, and the 1.0 times 10 to the minus 14th is the product. Acidic solutions, you see at the first acidic solution, you're down to 1.0 times 10 to the minus 2 molar. It's, I think I should point out that when you're working with negative exponents, you need to remember that the larger numbered quantity for a negative number, so if you're looking at 10 to the minus 7th molar there and 10 to the minus 2 molar, the acidic solution actually has Well, that's 5 orders of magnitude, so that's going to be, I believe, 100,000 times greater than, it is quite a lot larger than the 10 to the minus 7th. There's a lot more acid in that particular solution. And if you look at the hydroxide, where you've got 1 times 10 to the minus 7 going to the acidic solution, 1 times 10 to the minus 12, that's much, much less hydroxide. And you're always going to see that K sub W is still going to be equal to 1 times 10 to the minus 14th. Now, you should realize from this that if you're given the concentration of hydronium ion or the concentration of hydroxide ion, you can calculate the concentration of the other from this K sub W. So that, in fact, that's going to be one of the points of this particular section. And for the rest of the slide, the basic solutions, you see that the hydrogen ion concentration are getting to more negative powers of 10, which means there's less and less hydronium ion in their H3O plus and more hydroxide ion. Although the K sub W stays at 1 times 10 to the minus 14th. Now we're moving along fairly quickly here, but I'm going to spend some time doing some calculations after we get done with the instructional slides. All right, I already said that if you notice, K sub W is always a constant. We're at constant temperature, of course. It's 25 degrees Celsius. And the product of the hydronium ion concentration and hydroxide ion concentration is 1 times 10 to the minus 14th. So if you know one, you can calculate the other. And that's really the point where this slide is making. So if you have K sub W equal to the hydronium times the hydroxide concentrations, you can see hydroxide is going to be K sub W divided by the hydronium ion concentration. And I see I missed something there. Okay, it looks like I got that fixed. They left out some brackets there. So you see the concentration. It's just you have K sub W is equal to product of 2 terms. So whichever term you want to calculate, if you know the other one, you can simply do that division and you see what you get. And we're going to do some of that. So we're going to start with, here's the first problem. They're going to give you this calculation. What's the hydronium ion concentration if hydroxide ion concentration is 5 times 10 to the minus 8th? Okay, you're given 5 times 10 to the minus 8th molar, and you need the concentration of hydronium ion. So you know the relationship. The product of the 2 concentrations is 1 times 10 to the minus 14th. So that's that K sub W. So first thing you do is you write down the K sub W for water and solve for the unknown, which is going to be hydronium. And here you have 1 times 10 to the minus 14th divided by 5 times 10 to the minus 8th, 2 times 10 to the minus 7th molar, which gets close to neutral, but it's not neutral. So you have, it's a little bit higher, so it's a little bit acidic. It's an acidic mixture. So you have to look at that, and since you have higher than 10 to the minus 7th molar, you have 2 times 10 to the minus 7th molar, it's an acidic solution. So that's what you're looking for. Okay. We go to lemon juice, and it has hydronium ion concentration of 2 times 10 to the minus 3. What's the hydroxide ion concentration of the solution? Okay, well, there are a couple slides after this that actually do this problem, but let's get out the whiteboard and let's actually look at this and work it out the way we might do it on homework or a quiz. Well, for the second time in about 15 minutes, the thing stopped on me, so I've changed my internet hookup to a Ethernet cable, and hopefully this will work a little better this time. Let me make a little adjustment here. There we go. I got the whiteboard back, and here's the problem we're looking at. Let's go back here. The lemon juice has a hydrogen ion concentration of 2 times 10 to the minus 3. What's the hydroxide ion concentration of the solution? Okay, so let's work this out. Probably going to work a couple problems here since I've been asked to do things like that, and it's probably it's a reasonable enough request that I probably ought to do some more of it than I do, as I've said. In just a moment here, I got to find my stylus. Okay, here we go. So let's put down what we've been given, and now we know that. Okay, let's say we're doing this. I'm doing it slower than you're going to be doing it if you're under pressure, on a quiz or something like that. But you put down what you have here, and wait a minute, I got to readjust things here. Here we go. Okay, it's it's upside down. Okay, we're KW. You put these things down. You've got hydronium ion concentration at 2 times 10 to the minus 3 and fine hydroxyl. And the only other thing you really need is that this K sub W. So you have, okay, your hydrogen ion concentration times hydroxide ion concentration is equal to 1.0 times 10 to the minus 14th. Okay, so you know this. It's 2 times 10 to the minus third. And, well, if you want to work out this equation first, you want the hydroxide ion concentration. So that's what you have, that, and that's going to be 1 times 10 to the minus 14th divided by the hydronium ion concentration. Oh, I did things in the wrong order here. There we go. And we know what this is already, so we can just substitute that with this right here. Remember, that's hydronium ion concentration. It's that, so it's divided by 2.0 times 10 to the minus third molar. And now we get out our calculator, and let's 1e to the negative 14th divided by, I'm working on a calculator here, 2e to the minus third, and what I get is the hydroxide ion concentration is equal to 5.0 times 10 to the minus 12th. Now, does that make sense? Well, you look at what we have here. You've got an exponent of minus 14 here, and in the denominator you have an exponent on 10 of 10 to the minus 3. So this 1 over 10 to the minus 3, well, that's a positive. That's essentially going to be plus what? Essentially plus 3. Let's do an aside here. In fact, let me do something with this, make this bigger. We have, okay, we can look at it this way. I hope you can see what I'm doing here is legitimate. Times 10 to the minus 14th times 10 to the minus 3. This is going to be, this expression is going to be equal to 10 to the minus 14th times 10 cubed. Think about that. 1 over 10 to the minus 3 is 10 to the plus 3. So this is going to be 10 to the minus 11th, and and this is going to be 0.5. So it's 0.5 times 10 to the minus 11th, actually 0.50. We need two significant figures. And, well, this is not scientific notation. You have to move this decimal place over. So it's going to be 5.0. And you're going you're going to the left, so you're gonna, if you look at it, it's gonna be 5 times 10 to the minus 12. So it looks like we got the right answer. And I was kind of checking it along the way. Sometimes it helps if you look at this to see if the answer makes sense. If you can do it another way, if you have time to do it another way. All right. So what did we have here? We had okay, 5 times 10 to the minus. I think it's 5 times 10 to the minus 12th, I believe. You can see, okay, 5 times 10 to the minus 12th, and we forgot, we got to put molar here. Okay, this is our answer. Okay, so let's see what they get. 5 times 10 to the minus 12th. This is the answer that we're saying that we're picking. 5 times 10 to the minus 12th. And so let's go through this and see what they give. Okay, the problem is worked out the way we did it, essentially. And well, there's a 5 times 10 to the minus 12. The answer is C, but I noticed there's another error here. So let me fix this. This one, I thought I had gone through this, but I thought I had actually corrected this at one point, but obviously that was on another version of this. But let me take care of that. Okay, so here we have this thing fixed up now. So you see that lemon juice is, well, the concentration of hydroxide is 10 to the minus 12th, and I overlooked that they're asked, is this acidic or is it basic? Well, 10 to the minus 3 is larger than 10 to the minus 7th. Watch those negative exponents, because if you have a larger absolute value in a among negative exponents actually means a smaller number. So 2 times 10 to the minus third is quite a lot larger than 10 to the minus 7th, which would be neutral. So that's a higher concentration. So it's an acidic solution. All right, that's how that is worked. And let's just do a couple others. And what I'm going to do is I'm going to go into the book and I'm going to take some of these, and they're asking for, calculate the concentration of hydroxide. Well, we calculated the concentration of hydroxide there. So let's do a few more of these. Let's do 1031. Let's do 1031. Just go through those fairly quickly so you can see this. Let's clear this. Wait a minute. Let's go back here. I said to clear. There we go. Okay. 1031. We'll do some of these. And this is the same problem. It's just a couple of different situations here. We're going to have calculate the hydroxide ion concentration of each aqueous solution with the following concentration of hydrogen ion concentration. Okay, so we're going to calculate given the following aqueous solutions. And concentration of hydronium ion. You're given hydronium ion concentration. Okay, this is given. So we start with coffee. Let's write these things down. Coffee at 1 times 10 to the minus 5th, 1.0 times 10 to the minus 5th molar. be soap. And that's at 1.0 times 10 to the minus eighth. Do something. Hang on a second. I have a fabric glove for using on the whiteboard. Okay, and I'm looking at these things, and 10 to the minus eighth molar for soap, that's going to make a lot of sense. That makes sense because you can see that it's basic. See, cleanser. They're not asking you here to say whether it's acidic or basic, though, but okay, cleanser. If I'm spelling it right, 5 times 10 to the minus 10, 5.0 times 10 to the minus 10th molar. D, lemon juice. We already did lemon juice. Well, in the book, they give 2.5 times 10 to the minus second molar. Or does, that's interesting. Okay, that's lemon juice there, but we'll times 10 to the minus second molar. That lemon juice, that looks like it's a little more acidic than the other one, but then that could be that it's actually conceivable that maybe this lemon juice is more concentrated than the other one. That's a possibility. The other one might have been diluted a little bit. But okay, let's look at these things now and just look at whether these are acidic or basic. 10 to the minus fifth, these are all hydrogen ion concentrations here. Okay, these are all hydrogen ion concentrations. So 10 to the minus fifth is larger than 10 to the minus 7, so coffee is going to be acidic. Soap, 10 to the minus 8th, that's smaller. That's a tenth, roughly a tenth of the concentration of hydrogen ion concentration in pure water. So that's going to be basic. Cleanser 10 to the minus 10th, that's even lower than 10 to the minus 8th. So 10 to the minus 10th, that's getting pretty basic. That's even smaller than 10 to the minus 8th. So not 100th, but this maybe a 20th or something like that, somewhere around there, but it's still basic. And then 2.5 times 10 to the minus 2, well, that's going to be acidic. We already know lemon juice is acidic. Okay, so now let's do these numbers here. Okay, 1.5. Remember, we have the Kw is equal to the concentration of the hydrogen ion concentration times the hydroxide ion concentration, and that's equal to 1.0 times 10 to the minus 14th. And in all of these cases, you're actually looking for the concentration of hydroxide. So we can work through this concentration of hydroxide, and, well, to work this out, we're going to get concentration of hydroxide is going to be equal to 1.0 times 10 to the minus 14th over the hydrogen ion concentration. And it's going to be the same for all four of these things. So we just run through these things. So for A, you have, it's 1.0 times 10 to the minus 14th divided by 1.0 times 10 to the minus 5th. And you don't even have to get your calculator out. 1.0 times 10 to, it's going to be, it looks like it's going to be 10 to the, 10 to the, oh, that's 10 to the minus 14th. Good thing. Okay, so that's going to be equal to 1.0 times 10 to the minus 9th. is going to equal the hydroxide concentration. And so keep that in mind. B, well, let's move this thing up. Okay, B is soap. We have 1.0 times 10 to the minus 14th divided by soap, which is 1.0 times 10 to the minus 8th. And that looks like it's going to be 14 minus 8 is 6. So it's going to be 1.0 times 10 to the minus 6th is equal to the concentration of hydroxide. Okay, this is coffee. Notice this hydroxide concentration is actually larger. It's larger than 10 to the minus 7, so this is basic. Remember we said that it was basic, so that's going to be soap. C, cleanser, 1.0 times 10 to the minus 14th. Where are we here? 1 point divided by cleanser, 5.0 times 10 to the minus 10th. Okay, I'm not going to do this. I'm not going to eyeball this. I'm actually going to use the calculator for this. So we have 1e to the minus 14th divided by 5.0 e to the minus 10th. And this gives me that in decimal, but I want it in scientific. So I get 2.0 times 10 to the minus 5th is equal to the concentration of hydroxide there of cleanser. And we'll do the lemon juice here. We'll do the lemon juice here. It's going to be equal to 1.0 times lemon juice. Okay. 1.0 times 10 to the minus 14th. 10 to the minus 14th divided by 2.5 times 10 to the minus 2. And that's going to equal I get 4.0 times 10 to the minus 13th molar. Okay, that's for lemon juice. And so we have what we can do. I can take a look at what we got for the lemon juice. Here's the lemon juice. They get hydrogen at 2.0 times 10 to the, or no, I'm sorry, 5.0 times 10 to the minus 12th, and that's compared with 4 times 10 to the minus 13th here. That's looks like it's in fairly reasonable range. So we have the, that's how you're going to work all these the same way. And if you're given the concentration of hydroxide, which calculate the hydrogen concentration with the yeah, actually we have some acidic ones. Let's take a look and see what the answers were here, just to make sure I got these things right, because I'm kind of going through it fairly fast. Okay, all of that checks out. So we're calculating the hydroxide ion. Yeah, is it the hydroxide ion concentration? Calculate the hydroxide ion concentration for each aqueous solution given the hydrogen ion concentration or hydronium ion concentration. Okay, well, we can do this the other way. And 1033, we get the same type of thing here, except we're starting with, we're given, now 1033, you calculate hydrogen ion concentration given hydroxide ion concentration. You do it exactly the same way. Okay, K sub W is equal to 1.0 times 10 to the minus 14th, and that's equal to the concentration of hydrogen ion times the concentration of hydroxide ion. And now you want hydronium ion, hydrogen ion, so you're going to divide this by this, and when you work through that, you're going to see that H3O plus concentration is equal to 1.0 times 10 to the minus 14th. I forgot to put that 1 in there, didn't I? Let me erase that. Times 10 to the minus 14th. Let's get rid of that. That doesn't mean anything. Divided by the hydroxide ion concentration. It's exactly the same type of problem. So let's look through these. A, you have stomach acid, which is (2.5 times 10 to the minus 13th molar. 2.5 times 10 to the minus 13th molar. I have that right? 2.5, yep. Urine at 2.0 times 10 to the minus 9th molar. C, orange juice as 5.0 times 10 to the minus 11th molar. And pancreatic juice at 4.0 times 10 to the minus 9th molar. And these are all hydroxide ion concentrations, okay? Stomach acid, you've got a fairly low, you notice you've got a low hydroxide, you've got a low hydroxide ion concentration. It's, or wait a minute, that's 10 to the minus 4th hydroxide ion concentration. Oh, no, wait, these are hydroxide ion concentrations here. Now, wait a minute. See, I just caught myself. I caught myself doing something I've seen a lot of people do on homeworks. You're probably not going to see anything like that using the Pearson site, but I was actually mixing 1033 with 1032. So this stomach acid is actually 2.5 times 10 to the minus 13th, and there's 2.0 times 10 to the minus 9th. That's urine. Okay, that's urine. That's correct. And then orange juice, 5 times 10 to the minus 11. Okay. And bile. He said pancreatic juice. Okay, I was looking at the wrong one. 2.5 times 10 to the minus 6. Molar. That's another. You always pay attention to what you're doing. It's easy to lose sight of what you're doing and keep track of things. And you saw me lose track of that. But now we should be correct. So all you really need to do now, these are hydroxide ion concentrations here. So what you're going to have is stomach at 2.5 times 10 to the minus 13. So your hydrogen ion concentration is going to be equal to 1.0 times 10 to the minus 14th divided by 2.5 times 10 to the minus 13th. And that's, we'll work through that. And then this urine is going to be, well, I'll just work these out and then just put down the numbers. So 1 e to the minus 14th here divided by 2.5 e to the minus 13th that gives me, and I have to go to scientific notation. So I get 4.2. It would be 4.2 times 10 to the minus 2 molar, and that's pretty high stomach acid. Okay, that makes sense. So you notice I got suspicious when I had that 2.5 times 10 to what, minus fourth or something like that, and that kind of made me wonder. Urine, it's going to be, that one's going to be 1e to the minus 14th divided by 2.0e to the minus 9th, and that's going to give 5 times 10 to the minus 6, so that looks like it's a little acidic. 5.0 times 10 to the minus 6. Orange juice, now we have 1e to the minus 14th divided by 5e to the minus 11. And it looks like we're in the right order of magnitude here. 2.0 times 10 to the minus 4th. These are all molar. And last but not least, bile, which is let me do that again. I think I get 4.0 times 10 to the minus 9th. These are all molarities. This is all hydrogen ion here. Okay, these are all hydrogen ions concentration. And okay, we have okay, this is hydroxide ion concentration. This is the this is the concentration of right here, hydrogen ion for stomach acid. And let's take a quick look at the answers. See, you should be doing a lot of this. You have answers here, and you can look these things up and see if you did them right. And sometimes you'll actually get the book has a typo in it or something like that, but this is 1033. So, okay, stomach acid, it gives, for A, it gives 4.0 times 10 to the minus 2. I'll look at that shortly. 5.0 times 10 to the minus 6 molar for urine. 2.0 times 10 to the minus 4th for orange juice, and 4.0 times 10 to the minus 9th for bile. Now, I'm going to go back and check my work for the stomach acid, for the, I think it was the stomach acid, which was A 4.0. Let me do that. Okay, I went through this. I recalculated this. This was a mistake. This indeed does come out to 4.0 times 10 times 10 squared. Wait a minute. Let's these are, some of these are mistakes. What happens when you're hurrying? So that's why you get in the practice of doing a lot of these problems and going back and looking and checking your work. And the more you do that, the more you root out some of these mistakes. Okay, but these are the answers here. This one is going to be for stomach acid, 5.10 to the minus 6 for urine, 2.0 times 10 to the minus 4 for orange juice, then for bile acid, 10 to the minus 9th. And you see that the stomach acid is definitely very acidic, 4 fairly large number there. And urine, 10 to the minus 6, that's acidic. Orange juice is acidic. And this one is, what have I got here? 4.0 times 10 to the minus 9. All right, so those are, that's the way you do these. This is like, I stress working problems. I mean, you should be doing a lot of these problems. I know you focus on what the homework in on the Pearson site, but you really should do some of the stuff in the book as, think of it as calisthenics. Think of it as, or think of it as some, oh, some sort of practice. If you're practicing some kind of sport, some kind of technique, batting practice if you play baseball or softball. You you just get used to seeing these things, and the more of them you see, the more accurate you're going to get. This is so anyway. This is I'm going to call it quits now for 10.5. This has already been a lot longer than I expected it would be, but I know just watching me work problems is probably helpful. And you see, I did make some mistakes, but along the way, if you've done some of this, you start seeing patterns and you start seeing things that really don't look right. And you're going to see a lot of that as you get into biology and biochemistry. So you learn what you're looking to see is what's the normal pattern of how these things behave. If you've got a certain hydroxide ion concentration, what's the hydronium ion concentration? Well, you can kind of eyeball it and think, well, is this basic? Is this acidic? And roughly how much? You pick these things up with time. So there's a couple more slides here. We've already worked through this stuff, so we're already done with that. So this is it for section 10.5. And I think we've actually done quite a bit here. This went kind of long, but I did the lecture and a little bit of problem solving at the same time. So you can probably go through this and pick out what you really need. And we'll go on with the next couple of sections, and we'll be done.